Well, if there's a velocity field, there must be an acceleration field as well. So to fully describe the motion of our fluid, we also need the acceleration field. As with everything else you've seen, acceleration doesn't actually change in definition. It's still the derivative of the velocity with respect to time. The challenge that we run into is that the velocity is a function of position and time. In other words, the velocity is a function of x of t, y of t, and z of t. And that means that we need to take the derivative with respect to time of this business here. And so acceleration is equal to d by dt of v of x of t, y of t, and z of t. Of course, if you're going to take the derivative of a function, that means you've got to apply the chain rule of calculus, the chain rule. And so where we end up is that we're going to take the derivative with respect to time of these things, and we end up getting dv dt 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 plus dv dx dx dt, right? Applying the chain rule here. dv dy dy dt and dv dz dz dt, right? The derivative of velocity of x of t. We get this extra cross term here because we got to take the derivative with respect to x and then take the derivative of x with respect to t. That's the same as derivative with respect to t. So let's look at what just appeared. Well, dt dt, that's easy. This one here, that's just a 1. But it gets stranger over here. What's dx dt? Well, we just looked a minute ago in the velocity. That's our horizontal velocity component, u. Ditto here, dy dt, that's our vertical velocity, v, and w is our z direction velocity, w, dz dt. And so the velocity field, when we take the derivative of it, extra terms show up. And so our acceleration field, a of t, is equal to dv dt, that's this first one, plus u dv dx, that's this term, plus v dv dy, that's the y direction term, and then the z direction term is going to give us a w dv dz. Well, that's a little bit weird math, but turns out to be really helpful. So let's draw a box around this thing. We'll unpack it. Okay. First, I want to give you a new notation. This has a notation. We're going to call this the substantial derivative. We're going to use capital D's to represent this new version of taking the derivative of a vector. And so this is called either the material, or the substantial derivative, substantial derivative. And it's represented like so, d by dt. If you wanted to take the material, the substantial derivative of some vector quantity, it would be the derivative of that thing partial with respect to time, plus u, derivative of that thing with respect to x, plus v, derivative of that same thing with respect to y, w, derivative with respect to z. And so the acceleration field has this component dv dt, but it's also got components that have this u, v, and w that show up in them. And that's going to become really interesting in a minute.